Welcome to this explainer. Every time you pull out your smartphone to find a coffee shop or reroute around a traffic jam, you are instantly plugging into this incredibly complex, globally distributed network. It's almost like magic. But today, we're going to pull back the curtain and trace those glowing data transmission lines that connect our world, transforming all that raw geographic data into the seamless, interactive maps you use every single day.
Think of this as our futuristic heads-up display. We'll initialize these 6 core modules today to demystify the backend infrastructure. We're going to start with the geodata explosion, then look at speaking the same language, trace the client-server connection, break down delivering data via web services, explore the power of open data, and finally look at massive spatial data infrastructures.
Okay, part 1, the geodata explosion. Let's establish the massive modern challenge we're actually facing here.
Thanks to satellites, drones, and literally just the smartphones in our pockets, we are capturing the Earth in unprecedented, mind-boggling detail. The sheer volume of geodata and the number of maps on the internet, it's growing exponentially. But here is the major problem. Having mountains of data is kind of like having a sprawling library with billions of books, but absolutely no card catalog. How do we ensure quick search and easy access when this information is scattered across thousands of completely different, manufacturer-specific formats and distributed databases? Well, without a structured way to organize this chaotic fragmentation, the data is just trapped. It's entirely inaccessible for any practical use.
Which brings us to part 2, speaking the same language. To solve this digital chaos, we need the translators of the internet to step in.
The absolute bedrock of this solution is metadata. Simply put, it's data about data. Think of it as the ultimate sorting code for the entire digital network. According to our source material, metadata is structured in 3 really crucial ways. First, you've got its content. Is this a map of highways, or is it tracking regional rainfall? Second is its syntax, meaning the formal structure or format. Like, is it a simple JPEG image or a highly modifiable vector file? And third, it's pragmatics. This covers usability factors. Was this mapped yesterday or 10 years ago? And do you even have the legal right to use it? Standardized models like the ISO 11915 standard, which, by the way, consists of over 400 unique attributes, ensure that these wildly diverse, distributed databases can actually be searched and understood by anyone, anywhere.
But metadata alone isn't quite enough. We need universal standard setters to make sure everyone is speaking the exact same language. Enter the Open Geospatial Consortium, or OGC for short. Founded back in 1994, this nonprofit organization boasts over 500 members from across the tech industry, government administrations, and universities. What they do is create freely available interface specifications. The crucial takeaway here is their ultimate goal: interoperability. Much like how the tech industry had to finally agree on the standard USB plug so any device could connect to any computer, the OGC establishes the global rules of the road for mapping. Because of them, a database in Tokyo can seamlessly exchange geographic data with a server in London without hitting frustrating compatibility roadblocks.
All right, let's move to part 3, the client-server connection. Let's look at the delivery pipes.
So how does this actually play out in your everyday life? Well, we rely on a classic client-server architecture. On the user side, you have the client. This could be your web browser, a specialized geoportal, or heavy-duty GIS software. You, the user, define a spatial request, like zooming in on your local neighborhood. That request is transmitted via HTTP over the internet. On the other end, the server processes this request, pulls the exact necessary information from its vector or raster databases, and beams a response right back down the glowing network line straight to your screen. It is a constant, rapid-fire conversation of requests and responses happening in milliseconds, seamlessly giving you the map you need.
So part 4, delivering data via web services. What exactly is pulsing through those digital pipelines to make that fast-paced conversation happen?
This is where standardized geodata services, which are largely based on those OGC specifications we just talked about, really come into play. The crucial thing is knowing which standardized service is firing based on your intent. For example, if you just need a quick visual, like checking a live weather radar, the Web Map Service, or WMS, fires off. It regulates the fast display of geodata, delivering simple raster images like JPEGs or PNGs so you can see the map instantly. But what if you're an urban planner who needs to actually download and edit the specific borders of a property line? That is where the Web Feature Service, or WFS, steps in, sending you detailed modifiable vector data elements. Finally, if you need massive unedited datasets to run complex analyses, the Web Coverage Service, or WCS, delivers the complete coverage payload. It provides access to entire sets of data elements, usually as complex raster data. Together, they ensure the right type of data gets to you in the absolute most efficient way possible.
Moving right along to Part 5, the power of open data. As these transmission lines expanded globally, a massive shift occurred.
We entered the era of open data. No longer is mapping restricted solely to official government authorities or highly funded commercial ventures. Open data allows information to be freely accessible, modified, and distributed, usually under open licenses. A prime example here is OpenStreetMap, or OSM. This is a massive database built almost entirely by everyday people, what the industry calls volunteer geographic information. It's basically the Wikipedia of cartography. Anyone armed with cost-effective sensors like those built right into our smartphones can generate incredibly detailed, freely licensed geographic information and feed it directly into a shared, dynamic, global platform.
Now, looking at this impartially, the source material notes that user-generated open data brings fascinating benefits, but also some pretty unique hurdles. On the pro side, you get an unparalleled degree of up-to-dateness and immense thematic depth. Think about it. If a new road opens, a local user can map it that exact same day. It also beautifully captures unusual or subjective information that official maps might just completely miss. However, the cons are equally significant. Because literally anyone can contribute, the data often suffers from heterogeneous quality. What does that actually mean in practice? Well, an open map might have a meticulously mapped local hiking trail right next to a completely inaccurate neighborhood layout. Formats can be unstructured, and unlike official authoritative data, there is absolutely no guarantee of complete coverage or strict geometric accuracy. It's a fundamental trade-off, really, between rapid, rich crowdsourcing and official, uniform precision.
And finally, Part 6, Spatial Data Infrastructures. How do we weave all of this into one cohesive system?
The answer to this grand coordination challenge is spatial data infrastructures, or SDIs. An SDI isn't just a technical achievement, it's a structural one. Step 1 involves setting up the geodata alongside its descriptive metadata. Step 2 integrates those standardized OGC geodata services, the WMS, WFS, and WCS we discussed earlier. But Step 3 is the real game changer. It's establishing the crucial organizational and legal frameworks to allow safe, coordinated exchange. This is what allows countries to actually trust each other's data. These legal agreements power massive geoportals, like the GDIDE in Germany or the Inspire initiative across Europe, creating a seamless environment to monitor environmental and land management data right across national borders.
So we've successfully navigated the invisible web powering today's digital maps. We've uncovered the massive metadata sorting codes, the precise client-server pipelines, and the global standards that make the modern exchange of geodata possible. But I want to leave you with this final thought regarding the future of our ever-expanding, glowing digital Earth. As artificial intelligence integration deepens, and as distributed sensor networks expand exponentially, how will our spatial data infrastructures evolve? Will we soon see a world mapped not just accurately, but in absolute, living real time? It is a fascinating frontier to consider. Thank you so much for joining me on this explainer, and keep questioning the incredible digital infrastructure right at your fingertips.